Hey guys, this is my presentation on the mineraloid obsidian. So, what is obsidian? Specifically classifying it, obsidian is not actually a rock. It is actually a mineraloid. Now, what forms this mineraloid specifically? Well, felsic lava. See, here's a very important thing. Felsic lava, in what you might imagine lava as a hot spewing thing, is actually very, very difficult to find, which is why I pulled up this picture, because I'm not even sure if this is felsic lava itself, but essentially this is what felsic lava that cools into obsidian would look like. More specifically, this is what felsic lava that cools into Peel's hair obsidian, which we'll learn about later. That is what this more would be look like. Those little arcs, those are what might cool into the Peel's hair. What's more near the base, that flowing stuff, if that ever kind of touches the ocean, then that is more likely to form big chunks of obsidian. So, yep, there's the same explosion, and then it's gone bye-bye, because that is not exactly felsic lava. Anyways, so then what does felsic lava typically look like to us? Because we cannot really find felsic lava unless it's actively exploding, we can see cooled felsic lava, which is usually in the form of dacite. So you got this guy over here. This is actually a picture from I think it's St. Helens Mountain or something like that. This is one of the pikes. This specific thing, you can see it's kind of like this. That is because the lava is cooling under all that base mountain rock. It is cooling and being pushed upwards. That push upward is, but it's having a long time to cool, which is why you're seeing it as a big rock. This is dacite, which is a mix between rhyolite and andesite. And the reason why it's just a mix is because it's not physically mixed, but it identifies with the silica content, which is just how much silica is inside a rock. And so that silica content between rhyolite and andesite, it would fall between those two based on silica content alone. So that's what felsic lava looks like cooled. Now, what is more important about this felsic lava is its composition. Compared to other lavas, which I think there's like, I think something, it sounds like a bascolitic lava, and there's like Miraf lava. This is felsic lava. Felsic lava base form is typically comprised of, and I'm going to say these in order of how much they appear. This is going to be silica, which is those little beads on the left, oxygen, aluminum, and a banana. No, I'm kidding. It's potassium. That is what is more specifically inside of felsic lava. Now, the more important thing about felsic lava is how it more specifically cools, which is going to get you your difference between obsidian, which is such a cool gemstone, and the dacite that we saw on St. Helens Mountain Pike. So basically, the felsic lava, once it comes into contact with something, like if it cools really fast, so this would be like kind of like an example. The lava has time to cool extremely fast, not slowly, really fast. And so that is what forms obsidian, because it's not able to form a crystalline structure, which is basically the atoms. The atoms don't have time to arrange themselves inside the obsidian, so then they just form, I wouldn't say random, but they just form a structure that is not crystal, so it's not like octagons, hexagons, whatever you want to imagine it as. Which is why that is what turns this into obsidian. Now, I want you to take note of this obsidian here. It looks a bit dirty, but besides that, right near the bottom, I'm not going to put my mouse on the screen because I think bad things happen when that happens. But essentially, near that bottom of the obsidian, you can see a razor sharp edge. That is actually going to be really important for how that's basically really important, because essentially the crystalline structure helps make that to where I forget, I think it's called an amorphous glass is how it not really shatters, but fractures. It's called a conchoidal fracture, which essentially takes like curved chunks whenever you try and break the obsidian, and that's what forms those really really sharp edges. All right. So that's what obsidian is. So what about it? What about why is it so important that I'm noting this crystalline structure every like 5 seconds? Well, it's because it doesn't have a crystalline structure. It is, which means that it's not a mineral. That's why it's important, because this non-crystalline structure means that it is not a mineral. So then, why is it not being a mineral is important? Well, that basically makes it a mineraloid. A mineral is, apologies, a mineral is naturally occurring, inorganic, solid, has an ordered atomic structure. That is the crystalline structure I keep talking about. And it has a definite composition. Where obsidian fails to identify as a mineral is that it does not have an ordered atomic structure. However, this makes it perfect for making razor sharp edges. Why is it important that this can make razor sharp edges? Well, I'm going to read off something, and hopefully you'll understand. I might understand this. Obsidian breaks with the conchoidal fracture. So, I'm going to explain that just a little bit as far as I can know. You can kind of see in the arrowhead picture of obsidian, it has the breaks, the kind of like fractures on it are curved. That's basically what conchoidal fracture means. This means that it cracks in smooth, curved surfaces that are really sharp. Stone Age humans use this property to make arrowheads and cutting blades. Probably not like that, but something similar. Ancient peoples in Turkey began making obsidian tools over 10,000 years ago, very highly prized because they are very good. Were a major trading good. Beyond that, today we study obsidian by using hydrogen dating, which is essentially when freshly exposed obsidian touches the air and absorbs water to create a rind. Which is Scientists measure the thickness of this rind to calculate exactly when ancient humans crafted a tool. The stone is also used in modern medicine because obsidian holds an edge much sharper than steel. Some surgeons use obsidian scalpels for delicate eye and plastic surgeries. Yeah. Anyways, so if we continue on, we're going to talk about the obsidian family, which, I mean, there's more to this. By the way, I might note this now, just so that you all know the bias. This is a gemstone selling company, just to let you all know. That's where this image comes from, and that's where most of the information I got comes from. So I tried to make the bias go down and tried to report accurately. So this is the Obsidian family, and more on that now. So we're going to go ahead and do this quick run, unlike felsic lava, because felsic lava goes kind of slowly. Mahogany obsidian. It's red because it forms with the occlusions of iron. This obsidian can be found in the Glass Buttes area in Oregon. The next one is snowflake obsidian. As you see, it has this snowflake kind of pattern. This specific obsidian forms with inclusions of cristobalite and feldspar. This can also be found in the Glass Buttes area of Oregon. The next one is going to be a rainbow obsidian. Wow! Formed with the inclusions of magnetite, hematite, and feldspar. It can also be found in the Glass Buttes region of Oregon. The next one is green obsidian. This is not exactly a good image of green obsidian. Going backwards, the one on here, if there is one, which there isn't, how odd. Yeah, they did not put that on there. How odd. Green obsidian, but they did put it in their article, blog post, or whatever. This one is formed with the inclusions of iron, chromium, and notable iron and chromium. Its notable locations you can find it in are areas of volcanic activity in the United States, such as Oregon and California, and then there's Mexico, Guatemala, and Iceland. The next one is going to be our gold sheen obsidian. Why is it cut off there? It's going to be our gold sheen obsidian. This isn't a really good photo of gold sheen. It looks a lot more like a pearl. But essentially, gold sheen obsidian is formed with the inclusions of magnetite or hematite nanoparticles. It can be found in places such as the United States, like Oregon and California, Mexico, and various volcanic regions globally. The next one is going to be our silver sheen obsidian. This one has inclusions of magnetite or feldspar minerals, and it is found in parts of the United States such as Oregon and California, Mexico, and various volcanic regions around the world. Our next type of obsidian is going to be a midnight lace obsidian. This one, it has a distinctive lace patterns with midnight lace obsidian within the midnight lace obsidian as a result of natural fractures or cooling-induced stress within the volcanic glass, which is essentially, it doesn't well, it could, but it doesn't really have any special inclusions. It's just how it cools. This obsidian can be found in the United States, such as found in the United States, just as in states as Oregon and California, and it can also be found in Mexico, Iceland, and certain regions in Europe. Our next one is going to be the Peel's Tear Obsidian. This one is pretty cool because it is actually formed with basilitic lava. Essentially, if you think back, no, you don't even have to think back. I'll show you. First image. There we go. Oh, and yep, it's cooling. So if you look at the image, do you see those arcs, those orange arcs in the sky, which are those kind of upside down U's that go upwards and go back down? If those touch the water, then they could have a possibility of forming Peel's Tear, or maybe Pele's Peel's Tear Obsidian. Tear Obsidian. Essentially, this is just basaltic lava that is thrown into the air and drops back down into the water. It can be found more specifically in Hawaii, Iceland, Italy, Mexico, and certain regions of the United States. It is very thin and no. That is Peely's Tears. Sorry. And then this is Peely's Hair Obsidian. It looks like I didn't really write anything down for this. I'm not too sure how this stuff forms. I think it's more or less kind of the same as how Peely's Tear Obsidian forms, except it might be just like very, very, very thin strands. I saw this one image, and I wish I could pull it up, but it was kind of like a Peely's hair, except it had two of those hairs extending from it. So I'd imagine how that forms is it's the very, very thin trail behind a falling piece of lava. Anyways, that is going to be it for my presentation. And right here, I actually have a piece of obsidian I'd like you to observe, and I'd like to observe it too on the camera so that I can actually see what I'm doing. Hold on. There we go. This is my piece of obsidian that I have. Now you can see a bit better with the bright side. Can you? Not really. But look. It's very, very, pretty good sized piece. Look at that. I know on one side, if you see, where is it? On this side, it's, you might actually need the light for this one. On this side, it's very flat. Don't mind that. That's probably just like where they cut it. But as you can see, on here, you can actually see the little bits of difference in it. If I can kind of just go like that, so you can see a bit better. That is my piece of obsidian. And you know what? I'll bring y'all down here so you can see it too. Look at this. Excuse that, is my piece of obsidian right there. You can see it a lot worse, I guess, but look at that. All right. That is gonna be it for today's video. This is gonna be a first part. Whoa. This is gonna be a first part in a while series, but don't worry, all the other videos are still coming out, and I still have a lot of rocks to do. I still have a lot of minerals and whatnots to do. So yeah, I will see you all later. Bye.